What was I going to say? I've lost. Oh, so one of it is just the rework. Rework is a cycle. You got to try to stay away from that. And as you go forward, it definitely gets more costly because it's going to involve more people because you've got more paperwork, you've got more models, you also have physical parts. And the worst case is there are some cases where if you have to do a rework because how long it takes to build a part, it literally could be just a 9-month shift to the whole program because it could take that long just to build parts for an aircraft or an aircraft engine. It takes like, and of course we're in a panic trying to define what the part is, but once we do that, it's 9 months later. So you want to try to avoid that. Okay, so this is kind of the mode of we have less flexibility because we aren't thinking about what the initial need is. We have some issues of resource planning because we're just not planning for it. And development changes are very costly. So there's another mode that we try to get to, but it's very difficult because we're always balancing project needs, schedules, resources, so forth, so forth. And we're also trying to learn how to use modeling tools and simulation more. If we can present here with the customer, not only internal, but also internal stakeholders, say, okay, here's the parts that you have modeled. This is what they do when we stick them together. We start to understand better what the system is that we're starting to develop and validate that better. So now I can tell the customer, okay, look at this model. Is this what you want it to do? Does this fit inside your nacelle, this 3D model? Oh, no, that doesn't fit. You need to make an adjustment there. Oh, no, wait, it might be early enough now that he can make the adjustment too, because if you're doing this early enough, it's trade-offs on both. Later, there's not many trade-offs. You're in trouble. So, yeah. So you're trying to lead a lot of the modeling, simulation, and understanding ahead of starting to make parts. But then the nice thing is that part of the reason this research curve is so low down here, because you've done so good at defining everything, making those parts is a lot quicker. Because you really now understand. The designer doesn't have to guess, doesn't have to assume, doesn't have to run around so much. So your knowledge here has went up. You're basically hitting that time frame and design flexibility where you make changes much better and actually provide a better product. And your resource load is lower too. So you've actually got better resource control. Now the downside is this chunk usually delays a program. Programs don't like that. They want to meet a commitment. Because their commitment is usually based on they just have to reuse an engine for me, and let's have a new product. So we'll go to another slide that talks a little bit about what the impact of that is, which actually might be the next one. Yes. So this slide says I'm going to spend so much money on system engineering on a project. I'm going to have so much overrun as a result of the situation in terms of spend on system engineering versus the overall overrun on the budget. So if you notice, the less I spend on system engineering is the much higher my overrun is. And there's another slide on schedule in a minute. That's not a very good situation. But the neat thing is, if you look at here, it kind of stabilizes right there. So if I spend just that amount of money, I seem to have optimized at some point. Yes, it costs me this additional delta that I could have avoided in my original budget. But look at what risk you've mitigated. 200% or more versus, this is about 20, I think. Yeah, 20, whatever that number would be. A lot different. A lot different program, a lot different stress. Good question. I have a graph for that coming up. I like you. Which is this graph. Okay. So the green lines are different levels of complexity in terms, this is actually software code. So 10,000 lines, 100K versus 10K. So those green lines are representing different programs' complexity. So this, even though it says architect and risk resolution, it's really system engineering at the bottom that we're talking about. It's the equivalent of system engineering. So this is the percentage of time, now we're talking about schedule, not cost. This is the percentage of time that you're adding in because of the system engineering. And then this is the percent of the time added to overall schedule. So this is my delta to the schedule. So these what you want to find is these low points here, because that's where you've optimized spending money on system engineering and time versus the impact to the schedule overall. So for a very simple program, you don't have to do much system engineering. It's very simple and straightforward. My parallel of that, I used to be able to do everything in my head because everything was so simple. One controller, one person writing the code. Not nowadays. It gets more complex. Okay, well, if I got to find the right balance again, is this my spot? Where I just go all out on system engineering, I just end up in this straight line out here. That's the interesting part. Versus a very complex program where, man, it really goes up exponentially unless I apply system engineering down to here. Now, for me, most things aren't even in that ballpark. They're way past that in terms of complexity on jet engines. So, but this is trying to say there is a sweet spot. And again, the cost of rework kind of applies to that too. You know, the sooner you do system engineering, the less the cost of the rework. So it kind of tries to put that other aspect on there too. Okay, say it a little differently. I think I understand.
Like, because you did that system engineering beforehand, before you start producing, the cost of rework goes down because you don't have a likelihood of more.
It's not the cost of rework as much as avoiding the need for rework. Yeah. It is not possible to avoid all rework. It's called the unknown unknowns. How much time do you spend trying to figure out the unknown unknowns? But there's definitely plenty of known issues in the requirement, known issues in understanding of the system if we just recognize it and manage it. So this is more about, at this phase, if I have a rework, you know, that's going to be my average cost. Ideally, I want to avoid it altogether. I'm sorry, that's the other chart. This is more saying this is the average program cost based on I'm able to cut that rework out sooner. So there's some statistical number he's used from the study. So these are all papers, by the way. So this one I looked at. The other one I really want to go back and look at. So the key thing I want you guys to realize is this is not about applying system engineering. System engineering is cool, good. You know, you sit down, spend all day doing it. It's about applying system engineering in a practical manner to make the program a success. Success being I manage my costs the best I can, I've managed my risk, I've optimized my schedule, so forth, so forth. So I didn't bankrupt the company. It's always a good one. And companies have actually done that where they've gotten into, they're so far up here they can't get out of that cycle. We're so far off the cliff on the other end, they're in service, they can't fight the in-service problems in order to recover overall. We call it firefighting, and you hope the firefighting isn't so bad that you lose your job or the company goes bankrupt. You're in a constant wave of firefighting because of issues. And then maybe instead of being resolved, so engine programs are usually about 5 years. So we would spend 10 years trying to resolve problems and finally have the quality of product, as opposed to if we early on spent more time engineering it, it may have been more like 7 total. Because we still would have learned something in service engineering, but it would not have been nearly as costly, not nearly as late, and made the customer a lot happier. There is, yeah. The part of the balance is too is I got to get market share. I got to get market share. If I miss market share, I'm out of the business. It's sometimes it's part of the opposite pressure, but still that can be managed with a system engineer. So, okay, we realize that, but can we at least focus on these minimal methods to try to de-risk the best we can? Because that's the resources we have. What are the best use of the resources I can get?
So do you think it would be better to like launch a project that's like not the best but in the right market time, or like launch it later on when it's almost saturated?
Oh, now you're getting into all kinds of questions. See, how am I doing on time, actually? I'll tell you what, let's save that till the end if we have time, okay? Let me see if I can get to the rest of the slides. Actually, which I don't think I have that many more. So company culture, this is important for you guys. What is it about company culture that implies or manages system engineering is being applied? One is every engineer needs to have some kind of system engineering tools, background, capability. It needs to be kind of relevant to their job, relevant to who they're working with, but it really needs to be embedded in engineers. culturally, what I've seen happen is companies go through the firefighting mode. Why are we going through firefighting mode? Why can't we have products successful? Why isn't the customer happy? And they suddenly realize, oh, maybe we should need some system engineering. So a few people get involved in system engineering, come back, they come and say, oh yeah, here, put these things in, put these methods in. And then all of a sudden it becomes a department. Ooh, now we got a system engineering department. We're awesome, right? Still having problems though. And then what they morph into realizing, no, it's every engineer needs to have that culture of system engineer so we can talk among ourselves. We know we're kind of doing the same things. We're applying the methods. And then maybe have a few specialists that are really pushing, that's me, pushing the edge forward, trying to push the envelope forward. So that's where Rolls Royce is now. I mean, when I got there, it was specialist. And there was a few people that was out in the industry trying to figure out how to apply it. So now we don't even have a department called system engineering, but we have a few specialists like me. So I spend a lot of time working with teams. It's fun. I do a lot of training / sit down with the teams to counsel them on how to do their project. So again, back to what's the best way to apply system engineering methods in this case, not everything. We have internally, we have kind of a smorgasbord of options. That also, I guess the other point here, it needs to be reflected in your processes and procedures, which also align to our processes and procedures. Say, okay, if you're in this gate, then these are your options. If you're trying to collect requirements, these are your options. This is why you would use this one. Well, I don't have well-defined customer requirements. Well, you probably want to do this one then.
Do all those like look similar for different teams, or are they very different for unique teams?
So the way we've structured it is the concept is the same. What happens a lot of times, there's kind of like an appendix to say, okay, if you're in SDI or if you're in fuel pump design, this applies it at a better use case type level for you. So you're right, you got to kind of get down their practice level, but there is still kind of the generic overall one. So we still call it the same thing. It's just how you apply it to parts and what we call functional areas, which is more the emergent behavior of the system. So I put this quote here. So this is one of the guys in the UK that I work with a lot, and he's really done a lot for system engineering over time. Done a lot of papers. I put the quote here because the comments above was the section I was reading about company culture. So his comment is, the world increasingly relies and needs well-engineered, big-picture solutions. Engineering approaches are critical, I should have bowed that word, critical to ensuring that these solutions are produced as needed and effectively. So one of the previous slides also said, develop, produce, and retire. One of the things we try to make sure everybody realizes, system, product cycles are not just make a product and go away. It's someone's got to manage all the way through to the retirement. And the best way to do, part of the best way to do it is think up in the front, what are my requirements? Does that change my materials? Does that change my shipping? Does that change how I produce stuff? Again, companies are getting much more environmentally conscious. Well, there's also self-interest in there too. But so that's kind of the last of the use cases of system engineering. I had a few more slides here. One is trying to talk about the fact that all these organizations, I don't know, what major are you in? Computer science? Electrical. So you guys have different views, but you're using tools that are system engineering in some ways. You're still trying to think about what you're coding, right? You're still trying to think about what the circuit board is going to do. So all these societies, aerospace societies, IEEE, they always had aspects of system engineering in them. But they always had different views. So in COSI, which is International Council on System Engineering, which is where some of the slides are from, came together in 1990 recognizing, no, we really need to get the system engineering under wraps so that our groups can work together and think about the bigger system. We're not having these boundaries. So their focus is on that whole picture of system engineering. They're not a discipline, they're not a engineering major, they're just system engineering. How do we apply that? How do we work with all these different groups to move it forward? So that's the group that's really now society since 1990 that focuses on system engineering. Now, you guys may not have heard about it because it's usually the older people that realize the value of it. after you've been in industry. But it is a very good group. There's a local group in Annapolis that we meet once a month. So, okay, summary, take-home points. So I don't think I'm too bad on time. First off, the value of system engineering is growing quickly. If you look at some of the charts I had, the exponential aspect of complexity, time to market getting shorter, it's just going to get more important. It is not about doing system engineering. It's about applying the right system engineering aspects, methods to make the program a success. That's where experience comes in, that where things like in Cozy can help coach people through and understand what the cases are. These nice little graphs like this, a lot of those are in Cozy reports. Help us understand the trade-offs and balances. All engineers need some kind of understanding to support their job as system engineering. Doesn't mean you have to be an expert. Doesn't mean you need to take the system engineering test, but you need, at least your organization at some point should be moving toward everybody has to have some capability in that area. Now, I will say this, you may not see this when you go out and interview with companies. My observation, in fact, we was talking about this last night at our monthly group meeting or chapter meeting. Aerospace defense is way ahead of most in terms of system engineering. We're looking at models, we're looking at doing things without paper. Cummins Diesel, they're still doing paper stuff. But they're lagging about 15 years. It's not that they're not there, they're lagging about 15 years and starting to look at how to get there for the little impacts. Here's the problems we have. Can we apply system engineering? Where Rolls Royce is looking at more of, okay, now how do we make this system all interoperability, all tied together and working? In my mind, it's also how can I make it so the engineer just focuses on what he needs to do. Don't care about where the information is. He just finds the information. He goes in, that's the step I need to do. I need to apply this method, so where's my information? That's the world we're moving to. When you go out in industry, you'll find a mix. My takeaway is to make sure you realize it's important. Let's make the world a better place. Aha. And I think that is it. Questions and answers. I did want to mention there's 2 more sessions. Mike and Chris do a much better job talking than me. They've had a lot more practice in terms of speaking in front of people. I do a lot of interactive groups. So we're going to fodder up with SE processes and activities and SE principles. There's actually a paper that Chris wrote that they're dividing in half. They were giving me a hard time last night. This is actually the hardest of the 3 because we're used to writing about the other topics. The last one is, if anybody has suggestions, I'm looking for suggestions for the last one. I think the one we're playing with is asking how digitalization has impacted system engineering over time and where it's going. So I'll be getting into this, okay, what does system engineering look at previously, paper process, document-centric, MBSE type things, and how's that impacting the industry? So that's our thought for the last one. Okay, so your question, what was it again? Do you remember? I think I ended right on time too.
Yeah, I was wondering like the trade-off between like launching your product on time when like the right time in the market, and like taking time to develop the product really well, and then like launching it later when the market might almost be saturated.
Those are hard questions to ask. I will say the last one, you're not going to have a business if you're waiting for the market to be saturated, unless you have something very innovative. And think of Apple when I say that. That will disturb that market. You're not going to get marketplace. You got to have something very innovative once that market is saturated. Doing it early on may give you the business position to capture 8% of the market early on, but then you've got to manage the impact to the business. Is it worth that risk? And you also have to convince marketing it's worth the risk. You have to also convince marketing there is a risk. I said that the wrong way. What was the middle one? Giving it more time. That one's a little hard because you have to really like, what's the payoff and opportunity? So for large engine civil, and the other engines are just a different scale. Typically what happens is we do an engine development for 5 years. It takes 10 years to break even, okay? 10 years. So you've invested for 15 years before you even get money back. The Trent program may be more like 20 because of the problem it's had. So instead of going down that curve and then coming back to 0 and start making money after 10 years, It went down, started to come up, went down, up. So it's got a lot longer to go.
So in this situation, like, with
But, sorry.
Is it like better to like take more time because it's like you're taking 10 years to invest on it? So like even if you add like 2 more years for research, wouldn't like that be better than like starting all over again?
Again, this is all theoretical. It depends on what the payoff is at the end. If I can wait 2 years, and I know the other competitor is not mature enough and they're going to struggle for the market, maybe I want to be the one lagging because I know they're going to go through the not me. And actually, I think that's what GE did on us on that case. Usually GE was leading. We were really pushing hard to be the launch customer, launch engine on that aircraft. And as a result, we went into Boeing, did all the development with them, did all the interfaces with. We invested a lot more than GE did. Because when GE got to it, a lot of that was already defined and developed from the aircraft side. So there's always pros and cons. But from a Rolls Royce standpoint, it was a market. We wanted to get fodder in the market. Then we want to compete against GE. We want to be more than 50%. So that was the driver. The risk was the debt, the recovery time, so forth. So now the other aspect you mentioned, how do you, is it a delay? Sometimes it's not a delay. Sometimes you need to have people thinking about where are we going? Are we going to produce turbo engines the rest of our life, in our case? Or do we need to look at what the marketing trends are? Electrification is really big. Rolls-Royce is spending a lot of money in electrification right now because they know if they don't, they won't be a little player in that market because there's a lot of people playing in it now. Also, new technologies. We also look at our competitors and say, okay, this is the size engines they've got. Our engines have been great, but they're 30 years old. Those are going to be coming off wing being replaced by a competitor unless we have a replacement. So we start the R&D. But again, R&D costs money, so you got to be everything else profitable to go back into the R&D, new products. So there's a whole strategy here that's going on. So it's not an easy answer because there's literally a whole strategy and everything and balance of stakeholders. Do you have one?
I was going to say, so earlier you kind of mentioned how like one of the goals of system engineering is get that like systems knowledge up as quickly as possible in that chart. Do you think that has kind of like a negative impact on wanting to be like innovative? Because if you like stay close to where you've been before, your system knowledge is probably already like if you are just iterating off a previous like design.
Okay. Let me phrase it differently. He said system knowledge. I put a little note down there what that meant because that was a graph I copied. In reality, what they're trying to do is validate the need of the system. Is this the system I want to produce? To be innovative, you have to understand what the system is trying to produce to look at the trade-offs. So that earlier you can bring that in, the earlier you can look at innovative solutions and trade-offs. Trade-offs for weight, trade-offs for technology, trade-offs with your customer because your customer is going to be more flexible too at that point if it's an integration issue. So yes, that understanding goes up, but it's because you're trying to take that risk and uncertainty out, but it also gives the opportunity to be more flexible and more innovative at that time. As you go forward, I have parts made, you can't hardly be, if you're trying to be innovative at that point, it's because you can't figure out a right solution. It's not an easy solution to fix the problem at that stage in the game. I'll put it that way. And trust me, there's plenty of those. Because a lot of times we don't understand why the engine's operating at that point. So he's like, what do we do?
That's more of the firefighting kind of phase.
Yeah. There's plenty of innovation there because you've got to solve a problem that sometimes is very difficult. But that's not value added to the overall product if you're firefighting and reworking, as opposed to early on having clear requirements, so that wasn't even a consideration. Now, there's still unknowns, so no matter how you look at it. You still need at least 20%, so. Yeah. We don't like Murphy. One of the things, since we got a little bit more time, I went through the NCOSI handbook, which is this guy right here. And if you're really bored and want to study it and take a system certification test, you can. It has section titles, which are very unclear what they actually mean. But what I did was I went through the EPICS, things that you guys do. So semester plan, design review, you've got this nice little process cycle. And kind of went through the descriptions of those sections. And there's a part of what you guys are doing, in all those sections. Yeah, you're not doing it to the same, actually not even close to the same level. But it's getting your minds to start thinking about things like that. Just to have this and be thinking about these cycles and going back and forth and how that works is a big step. Things that I didn't have. Which actually reminds me, I was supposed to say that I was here at EPICS from the beginning, but actually I was here the second semester. Because usually Bill introduced me as the person who's been most involved in EPICS all of his life. So I also came back as a factory advisor, and now I'm doing this again. So I'd love to come back and do factory advisor, but with my technical role now, I get up at 4 in the morning, and it's exhausting. So EPICS is giving you at least some aspects of that. It was the point of that slide. And okay, so that is all I have, unless you want me to try to give you stories about engines or something. I have plenty of good stories if I can get back to that slide. Oops, not that one. Of things that can go wrong and right. And these are some good use cases. So I'll leave it up to you guys. I think the time is over, but I'm happy to keep talking a little bit. Since neither one of you are budging, I'll talk. Well, some of these are actually the positive things. So I'll go through these. Trent 1000, 787. Anybody know what the newest Boeing airliner is? The 787 all-composite fuselage. So this is also the engine I said that had a problem. This is our test aircraft, but that's the engine that goes into that aircraft. Biggest issue is you had a lot of good specialists. Part of it's a culture too in that site. Culture was, this is my job, that's all I do. This is my job, that's all I do. So they didn't have anything to do. They went off and did more research, more studies. This is all I need to do. They didn't have somebody saying, okay, well, let me broaden my skills. Let me understand the system more. And plus, they really didn't have that good system taught. It's on the 4th variant because they still haven't got it right. Sorry, 4th version because they still haven't met the requirements. In this case, it was really hard to fight that culture. But they are learning to change as a result of complete failure. And they're using a lot of us to help give them guidance. So. This is an interesting one, Global Hawk. You guys know what Global Hawk is? Or is it just my generation? Okay. So this thing has a wingspan as big as a 737 and about the length of 2 cars. In the back of that is an AE 3007 engine that we produced down in Annapolis. When I came on that program, it still hadn't even been tested. It was just kind of still a wish list for the Air Force because, hey, we want a vehicle to go up there and fly and stay up there. And then the Iraq War came. We flew that thing before it had been tested for safety and all this stuff. You know, we had some basic understanding. Officers like, give us your safety report. We need to see if we need to fix anything urgently. We want to go fly this thing. So this thing would fly for 48 hours, leave U.S., fly over to Iraq, and survey an area the size of Indiana and come back. All on its own. This one truly was autonomous. You didn't have to, unlike the Predator, where a person tells it, works the takeoff, and then it cruises a spot, and then the person has to fly it around. This one, they just launch it. They woke up and see the video. That's all they had to do. But downside of that, well, first off, there was nobody on it, so that made it easier. They could justify it. And also the urgency of the war. They did lose a few because they didn't quite have the system integrated for the environment. This thing flew at 65,000 to 70,000 feet. The engine wasn't originally made for that. Requirements don't match anything, but we did enough testing. Well, it should survive for the most part. We haven't qualified it to do that, which later came, and now it's a real production part, so a production aircraft. Again, urgency, payoff. CI needed it, military needed it. It was good enough. The risk is it becomes a missile. Actually, the sensitive part is all the electronics in it for surveillance. So there's explosive bolts on the side that blows the whole thing apart. The other option is it will do a nosedive into the ground. When they were testing one of them out in Edwards, they had one flying, and they had another test facility that was testing the electronics. Again, this is so early on, they're just trying to get it out there. They sent the self-destruct command in the test lab. The aircraft went, didn't have explosives on, but it nosedived. So that's the first one they lost. Well,